I wonder why you didn't pop up. Huh. That's weird. Where am I? Huh, that's just weird. Okay, so we're recording and it's recording all my confusion. Good. All right, so at the end of class last week, I threw a bunch of junk at you and I said there was a worksheet on Canvas in the chapter 8 radicals and roots section that had all these rules printed out for you, and I really hope you printed them out. But just to make sure, for all your final answers, remember, in the middle of a problem, you can violate all kinds of rules. But when you're done, you have to always ask, is my radical completely simplified to the best of my ability? Okay. No fractions inside of a radical, no decimals. Now, what that means is you can't have like the cube root of 3/5. That's a fraction. You got to somehow fix it. Okay. You can't have the 4th root of 2.75. Okay. Somehow or other, you got to figure out how to fix it. So, and we've talked a little bit about how to do that. We'll review that a little bit more tonight. But no fractions, no decimals inside your final radical answer. And lastly, no radical in the denominator. No radical in the denominator. Okay, those are some of our fundamental rules that we have to go over. I need to erase the board to make room, but I just wanted to make sure everybody's got them at least once. This should be in your notes from last week also in class. The basic rules we have is the nth root of the nth power always cancels out. The nth root and the nth power always cancel out to make just x. Okay, to be really legit, sometimes the x needs an absolute value around it, but I've made sure that all questions don't require an absolute value. Even on the test, it says all answers are real numbers, don't use an absolute value, or so, it says something like that. So don't worry about it. I know the book pushes that, and that's actually proper. I'm trying to keep things simpler than that. So I'll erase the absolute value there. We can take apart a multiplication radical. Okay. If 2 things or more, 3 or 4 or 5 things are being multiplied together, we can take them apart into a bunch of separate little baby radicals if we wish. You don't have to do this, but you're allowed to do this. The double arrowhead is a bidirectional arrow. It means not only can you go from a single radical and split it up into 2, but you can go from 2 radicals and combine it back into 1. It's kind of like whatever helps you. You can put it together or take it apart if it's multiplication. A similar idea with division. You don't like the fraction, you can take it apart. Okay, or if you don't like it as 2 separate radicals, okay, you can put it back together into 1 big radical, whatever. Okay. Keep in mind, all of these assume that it's the same index. Okay. Cube root of A, cube root of B. Then you can put them together into cube root of A over B. And a couple of other things. Again, this was on that paper that I urged you to print out. If you haven't already, I really urge you to do this. You can never, hence the capital letters and the exclamation mark, you can never take apart an addition or subtraction radical. Ever. That just, I stopped grading. It's so completely wrong at that point. Nothing you do from that point onward can possibly be correct. So I stop grading if I see that mistake. You can never take apart an addition or subtraction radical like that. Okay? You can never take apart an addition or subtraction. I should have put a subtraction symbol up here. I'm sorry. Okay. There, power problem. Okay. Example. Suppose you had 2x plus 5 quantity squared. That never equals 2x squared plus 5 squared. Never, ever. It does not. Okay. We've talked about foiling or building the matrix for this one down here. The box, the matrix box, whatever. That's the only way to do it. Either foiling, if you know what that means, or building the matrix box. Okay, but you can't distribute this power into everything if there's a plus or a minus sign there. Okay, again, a great way to get me to just to stop grading. Okay, because again, if you make this mistake, if you distribute the power over the plus or minus sign, everything from that point onward is wrong. So be careful. And again, these were listed on that paper I told you guys about. Okay, I need to erase this to make room for a few review questions and some new stuff. I also need to talk about this coming Thursday. We will have count them, two quizzes on Thursday. Don't panic. Don't panic, okay? The first quiz will be about 10 or 11 questions in class on Thursday. Okay, the second quiz will be available Thursday night on Mom, but not due until Monday, the following Monday. So on Thursday, we'll take quiz number 1 in class, and you'll have quiz number 2, which will be due over the weekend. You'll have the entire weekend, but it will be available to you starting Thursday night. I sent out an email last week asking you guys to evaluate me. And I said, if you did, then email me back and tell me you turned in the evaluation, and I will give you bonus points on the next exam. There is absolutely no way I can tell who has or has not evaluated me. I can't tell. Okay. They may ask you to type in your ID number, your student ID number, but that never comes back to me, ever. I get the overall results for however many people evaluated me, and it shows me certain scores in certain areas. It does tell me what the comments were if you wrote comments, but other than that, I don't know who you are. So this is totally anonymous. Okay. It's I'm asking you to, but if you don't, I understand that also. Also, newest grades are online. Check them out. They include your last quiz and your chapter 8 elementary homework. So check all that stuff out. All right, I want to erase all of this and start doing some problems. Anybody have any questions about what I've written or what I've said?
Are you going to take the quiz on the second half of the class?
Yes, at the very end of the class, so that those people who finish early can go home, and those people who need a little bit more time can take the time.
Are these quizzes on the same topics?
No. Quiz number 1, I think if you go into Mom, I think it gives you a brief explanation, but it's simplify, multiply, divide, simplify, multiply, add, and subtract radicals. Simplify, multiply, add, or subtract. That's quiz number 1. Quiz number 2 is the rest of the chapter. Quiz number 2 is rationalize the denominator, division, basically. and solving equations. Okay, good question. Thank you. Anybody else?
Are they both going to be on mom, or one's paper and then the other
No,
one's on
the
mom?
first one is paper, and it's going to be at the end of class on Thursday. The second one is on mom. Anyone else? Okay, let me erase, let me pause the. We said one of the major rules is you can have no radical in the denominator. And this leads us to the process that's called rationalize. Why do I keep picking up the wrong pen? The denominator. Okay, that's what the process is called. So I'm going to do 2, and then I have 2 or 3 for you to do. The first one that I want to do as a reminder is 8. Just to review, 8 radical 18 over 12 radical 10. Now, when I say radical, one of the things you guys need to know is that when we write a radical with no index, it's assumed to be a square root. Okay, if I want it to be anything else, I have to write the index, the cube root, the 4th root, 5th root. Okay, that's number 1. Number 2, one of the first things we learned on division of radicals was to divide inside with inside and outside with outside. Just reduce them to the best of your ability. Inside reduces with inside, outside reduces with outside. So if I were to do this, I would say 8/12 reduces to 2 over 3, because you can divide 4 goes into 8, 4 goes into 12. But what about 18/10? Well, you can reduce that also into the square root of 9 over the square root of 5. So you can reduce or cancel or whatever you want to call it, outside with outside, inside with inside. Do you have to? No. Is it easier? Usually, yes. Okay, because you're working with smaller numbers, and that's always a benefit. Now, a little bit more here. Okay, turns out you should be looking at the square root of 9 and going, oh man, that's 3. Okay, that's even nicer. So this becomes 2 times 3. This is 6 over 3 radical 5. Okay, is that okay with everybody? We're not done with this. We're not done. But so far, do you understand my steps? Simple reducing, inside, inside, outside, outside. In fact, the square root of 9 is a 3. So you have 2 times 3, which is 6 on top. That okay with everybody? Okay, then what we look here, we go, okay, I've done everything right, but I'm in violation of the rule that says I can't have a radical in the denominator. I'm in violation of that rule. When it was a square root, okay, there's a lazy way to do it, and it's fine. I don't use lazy as a negative thing. I use it as a shortcut. If we just simply multiply top and bottom by the square root of 5, okay, so you use the radical 5 to help you, okay, you end up with 6 radical 5 over. Now, I'm not sure why this happens. It's happened in the past, and a couple people talked to me or emailed me over the weekend. For some reason, people go the square root of 5 and the square root of 5 cancel each other out. Look what I wrote. People take this problem, multiply top and bottom by radical 5. Yeah, that's good. And they say I have 6 radical 5 on top and 3 on bottom. And there's this belief somehow that the radical 5 times the radical 5 cancel out. No, they don't. They do not cancel out. And I don't know where that comes from. I have no idea, but I've seen it over the years. A lot of people do that. What happens is you end up with 3 radical 25, because when you multiply radicals, you go inside, and the square root of 25 is 5. So you end up with 6 radical 5 over 15. 3 times 5 is 15. Last thing, 6 and 15 reduce. 3 goes into 6 2 times. 3 goes into 15 5 times. That's the final answer. So they still keep reducing. There might have been a secondary way to do this problem, but your steps would be pretty much what my steps are here, so it's okay. Any questions about anything I did here? Okay, this is kind of a combination of what we did last week on, I think it was Tuesday, and then we continued it into Thursday. Rationalize the denominator. And when it was a square root, it's real easy to fix it. Real easy to fix it. Okay, just multiply the denominator by itself. So any questions on that example? Okay, then moving on to a different example. What if we had oops. What if I had 5x on top, and on bottom, I had the cube root of 4x squared y z squared? Okay, again, the basic rule says for your final answer, you can have no radical in the denominator. No square root, no cube root, no nothing. You've got to get rid of all of that radical. Okay, the problem gets a lot more complicated when it's cube roots and fourth roots and stuff like that. So what the way I showed this is I said we want this to be everybody cubed in here. We want everything in here to be x cubed, y cubed, z cubed, and maybe even 4 cubed. I don't know. Everything has to be cubed because that's the only thing that comes out of a cube root. So we have to go from the original problem, do some magic to it, some math magic, to make it look so everybody's cubed. Now, this particular problem had a little trick that I want to make sure we pick up. Instead of 4, I see 2 squared times x squared times y times z squared. Okay, I want to look at everything in terms of factoring, breaking it down. So then we said, okay, I want to make everybody cubes. What do I need to multiply by this to make it kind of look like this? So I need to multiply top and bottom by a 2. Oops, this is cube root. Come on. Because I have 2, so I need one more to get 3 of them. I need a single x to top and bottom because I have 2. I need one more to get 3 of them. I need 2 y's, y squared. Excuse me, y squared. I have 1. I need 2 more to get 3 of them. Okay. And I have 2 z's, so I need a single z to get 3 of them. So what happened is my new numerator is 5x times the cube root of 2x y squared z all over the cube root of 2 cubed x cubed y cubed z cubed. I made everybody in my denominator a cube somehow. And what you have to do is accept that it screws up the numerator. But the rule says no radical in the denominator. Later in other math courses, you'll find it convenient to get rid of radicals in the numerator instead. And they'll show you how to do that. So sometimes, most of the time, we don't like a radical in the denominator. Okay. Some of the time we don't like it in the numerator, but you use the same process, same idea. Okay, so what do I have? Now let me erase this. Okay, where's my glare? Okay, so I have 5x cube root of 2xy squared z on top. On bottom, all of these come out, 2 and an x and a y and a z. Remember, when cube powers, if you take 2 cubed out of a cube root, you just get 2. That's the rule that we're using. What I said the other day is when you pull it out, it loses its power, and that's actually what happened. If you took the cube root of 2 cubed, you just get 2 by that basic rule that we use. If you have the cube root of x cubed, you just get x. And so that's kind of what we're doing here. Now, we're not quite done. We're not quite done because this x and this x happen to just cancel each other out. Oh, good. I looked at the glare and I ignored it. So anyway, this x and this x cancel out. So our final answer is 5 cube root of 2xy squared z over 2yz. That is our final answer. Okay, so I've done 2 problems. One is a square root, one is a cube root. Yes, these will be on the mom quiz that's due over the weekend. Absolutely, these will be on exam number 2. Absolutely, no getting around that. So, any questions about either of these 2 examples? Do you want me to explain it differently, better, slower, anything?
A little bit slower.
Pardon me?
A little bit slower.
Where, what part?
I got everything, but just like the next problem, just a little bit slower.
Okay, all right,
Yeah.
fair enough.
Thank you.
Okay, anybody else? All right, Well, it turns out that the next problem is going to be one you're going to try and do. So I need to erase all this. So I hope you guys have copied it. And okay. So I want you guys to try this problem. 7xy over the fourth root of 8x squared y squared z, and this one 3 nuts over the fifth root of 81x to the third. Okay, so for the first problem, we have a fourth root, which means I want to get everything inside to be fourth powers. But before I do that, I've had enough experience now. I know 8 somehow breaks down. So this problem is the same as 7xy over the fourth root of 2 to the third, which is 8. And if you didn't know that, you can go off to the side and do a little factor tree. 8 breaks down to 4 times 2, but 4 breaks down to 2 times 2 times 2. So we know that 8 is 2 to the third. But if you've been doing your homework a lot, that just keeps coming up over and over and over again. Then we have x to the second, y to the second, z, okay? So now I need to get fourth powers. I need to turn everybody in here into a fourth power. So I'm going to multiply this by the fourth root of, I need a 2, I need an x squared, I need a y squared, and I need a z to the third. And I need to do the same thing to top and bottom. Okay. And that's the magic. That's the hardest part of this, as far as I'm concerned, is where does this junk in red come from? It's not something that I just made up. I know that this times this makes fourth powers of everything. Is that okay with everybody? Anybody have any hesitation on that? Where this red radical came from?
I do. I don't understand that part. How does the squared become
Well,
four? Like,
okay, because in my mind, I'm putting these together and I know that I have 2 to the third times 2 to the first, so I have 2 to the fourth.
so
And I have
3 times 1 is 4? Like, do you, the
no. When
powers,
you
so you add them.
Yeah, that's back to chapter 4 or 5.
Okay,
When you're
okay, that's where I was
multiplying with the same,
confused.
okay, same base, you add the powers. The only time you multiply powers is if you had a power raised to another power. If you have a power raised to a power, that's when you multiply.
Okay, got it.
Okay,
Thank you.
so that's I'm taking advantage of that rule there, that you keep the base, add the powers. Anybody else? Okay, so on top, I have 7xy times the fourth root of this mess, whatever it is, 2x squared, y squared, z cubed. It won't simplify because these are, they have to be fourth powers to get out of a fourth root. They're not, so they're just going to be in there and they're going to be ugly. That's just kind of it. Now, some of you can skip this step. I encourage you not to, because this is like a check. What do I have? I have 2 to the fourth. It will come out on my next step. I have x to the fourth because these two here, you add the powers. I have y to the fourth and I have z to the fourth. That's what you're shooting for. If you don't have everything is fourth powers in this problem, then it's not going to work. So I accept that some of you can skip that step. I understand. But I would hope that you wouldn't, simply because that's kind of a built-in check. Okay, do I really have fourth powers? So because they're all fourth powers, this becomes 7xy fourth root of 2x squared, y squared, z cubed. Now they come out, a 2 comes out of the fourth root, an x comes out, a y comes out, a z comes out. Now all of them come out. And then I go, oh, but look. This x cancels, this y cancels. Okay, and again, we did those way back in chapter, I think it was 4, wherever we did exponents the first time, where you had a bunch of x's on top and the x's on bottom, and they did all kinds of canceling out. That's all we're doing. Same thing we did previously. So final answer for this problem. 7 fourth root of 2x squared, y squared, z to the third over 2z. And that would be my final answer right there. Is that okay with everybody? Okay. So back over here to this one, this is a fifth root. We haven't done a fifth root, I don't believe. Okay. So same thing with the 81. Remember over here, I took the 8 and I broke it down. I looked inside of 8 and said, wow, this comes some powers. 8 can be written as 2 to the third power. Well, 81, if you go to your scratch paper, 81 we know is 9 times 9. So, and this 9 can be 3 times 3, and this 9 is 3 times 3. So I know that 81 is 3 to the fourth power. Excuse me, I shouldn't say I know. I figured out that 81 is 3 to the fourth power. So my original problem is really 3, gosh, come on, dummy. It's really 3 over the fifth root of 3 to the fourth power times x to the third power.
We have a question.
Yeah.
It's in also 81, 9 square.
Yeah, but you're worried about fifth powers.
Yeah, I did that and then I multiplied it by 9 to the third.
Oh, I see what you did. But then your answer, you would have to reduce it later.
I did, so I think, okay, I just want to see where this goes.
Yeah. Okay. If you ultimately reduced your answer later, then yes, we're both the same.
right.
You're not, your method isn't wrong. Okay. I would say, well, you have a calculator. Okay. Never mind. I won't say anything yet. So like you, let's just see where this goes. So breaking 3 down, this is 3 to the 4th. So what do I need? I need the 5th root. I need 5 of them. I have 4 3s. I need another 3. Okay. I have 3 x's. I need 2 more x's. So now I know that altogether I have 3 to the 5th and x to the 5th on bottom, but I have to multiply top by the same amount, 3 to the 3 x squared. So what I have here is 3 times the 5th root of 3x squared on top. On bottom, again, this is a step I like. A lot of students don't. I have 3 to the 5th, x to the 5th. That's like, for me, my built-in check. Do I really have 5th powers inside of a 5th root? Because if I don't, I can't go further. Okay, so those come out now. So I have 3 times the 5th root of 3x squared over the 3 comes out, the x comes out. Okay, my 3z's will cancel. So my final answer is the 5th root of 3x squared over x. Okay, did you get the same answer?
I think I almost got there, but I needed to simplify more to get there.
Right. So by my picking a smaller number here, I didn't have to simplify as much at the end. By your going to 9 squared and then multiplying it by 9 cubed, you had more simplification to do. Wouldn't be wrong. It has to come out the same way, assuming you didn't make a mistake, but you're okay. You probably had the 5th. Somewhere in here, you had the 5th root of 9 to the 3rd. Somewhere in your work, in the numerator, you had the 5th root of 9 to the 3rd.
Yeah, I think that the 9 to the 3rd simplifies to like 3 to the 6th, and then I
Bingo.
get 3x squared.
And that's how you get the x's out. Yes, that is correct. Okay. All right. So, I'm going to leave these and move on to a new topic, kind of related to this. This is simplifying radical denominators, square roots, cube roots, 4th roots. Again, I promise this will be on quiz number 2. I promise it will be on exam number 2. Guaranteed. Any questions on this? Okay. Then we had to do some thinking here. And all of these examples have been examples of what were called monomial denominators, 5 over the square root of 7. Okay, you had a single thing in the denominator, and so to fix it, okay, you had to multiply top and bottom by the square root of 7. Remember, it's a square root, so we can afford to be lazy. Just multiply top and bottom by that same thing. So we have 5 times the square root of 7 over the square root of 49. So that's 5 square roots of 7 over 7. Okay, And those are called monomial, mono meaning one. There's one thing in the denominator. There's one radical down there, or one thing. Okay. Oh, I do want to make a point. Okay, I hope everyone sees that the radical 7 and the regular 7 don't cancel at all. They don't have anything to do with each other. They can't cancel each other. Radical 7, regular 7 don't do anything to each other. They're just separate. I think we had a problem over here where we have the 5th root of x over x. They don't do anything. You can't go anywhere. This x is trapped inside the radical, and this is not inside a radical. And we made a big deal about same index and all that kind of stuff. Well, those don't even have, this bottom one doesn't even have an index to be the same with. So please be careful. Radical 7 and regular 7 don't cancel. All right, that's called a monomial denominator. Well, we learned last week a binomial denominator. 2 over the square root of 3 plus, well, I'll be nice first time, 7. Yeah, that'll be okay. This is a binomial denominator. Bi means 2. There's 2 numbers here separated by a plus or a minus. Okay. The only way to clean this up, and I can't stress that enough, the only way is to multiply by what's called its conjugate. Good spelling. conjugate, conjugate. Okay, and that is square root of 3 minus 7 to top and bottom. Okay, I can't stress that enough. Okay, you as the student must recognize that the denominator is a binomial, and the only way to fix a binomial is with another binomial. The only way to fix a monomial is with a monomial. All right, back to this problem. Most of us can distribute the 2 here. So we get 2 radical 3 minus 14 on top. But you have to multiply these 2 together. And the only way to do it, well, actually, some of you may have found a trick. There is a trick way, but if you go back to our matrix, the square root of 3, 7, the square root of 3, minus 7. Square root of 3, positive 7, square root of 3, minus 7. Okay. Square root of 3 is square root of 9, which becomes regular 3. Square root of 3 times negative 7 is negative 7 square roots of 3. This will be positive 7 square roots of 3. 7 times radical 3 is that. 7 times 7 is negative 49. So what happens here is these 2 cancel each other out. One's a positive, one's a negative. They're gone. So the problem becomes 3 minus 49 or negative 46. And that's the answer to this problem. So monomial denominators have a special technique for fixing a monomial denominator. Binomial denominators have their own technique. Okay, for fixing a binomial. We call this the conjugate. Notice these two numbers are exactly the same, radical 3 and 7, but one of these is a plus, one of these is a minus. And then whatever you multiply to the bottom, you do the same thing to the top. Is that okay with that example for everybody?
I got a question.
Sure.
You can't simplify the 14/46 because it's the binomial.
And yes, and remember this is assumed to be well, actually, we could simplify it. Shoot, good question. I made a mistake. To answer your question, no, 14/46 doesn't reduce. My mistake is the whole problem reduces. Okay, let me show you what I'm talking about, like an idiot. Can I divide everything in the top by 2? Okay, this is a regular normal 2. And the answer is yes, I can. So this becomes the square root of 3 minus 7. 2 into here, 2 into here. Can I divide everything in the bottom by 2? Yes, I can. Negative 23. Okay. So to answer your question, no, you can't just reduce part of it. Okay. You must reduce all of it. So you had to divide the 2 and the 14 both by a 2 and the 46 by a 2. Okay. And without your question, I would have gone off and left this unreduced, unsimplified. Does that kind of answer your question or not?
Yes,
I-
thank you.
Okay. Yeah, no, I thank you because I would have walked off and totally forgotten about trying to simplify it, because most of the time these don't simplify. They're so ugly, they just don't. But apparently I'm not thinking. Is that okay with everybody? Okay. Are you guys okay with the multiplication over here by whatever method you use? Again, some of you use FOIL, some of you like this matrix box, doesn't matter. Okay. One of the cool things though is you have to remember when you multiply by the conjugate, the middle terms will always cancel each other out. Always. So that might lead to kind of a shortcut for some of you to think of. Okay, let's write this here. So this becomes the square root of 3 minus 7 over negative 23. Okay, so I want you guys to try this one. Five radical 2 over square root of 6 plus square root of 5. Yeah. Okay. Try that one. Okay. So the conjugate is the square root of 6 minus the square root of 5. Again, the conjugate is the same binomial, square root of 6, square root of 5, but one of them is a plus, one of them is a minus. That's all it is. And then you multiply top and bottom by whatever the new thing is. The numerator, you're going to distribute this here, and you're going to use, because you're multiplying, distributive property means multiplication. So because you're multiplying a radical, you're using the outside, inside rule. So on top, you're going to end up with 5 radical 12 minus 5 radical 10. That's on top when you do outside, outside, inside, inside to this, outside, outside, inside, inside to this. That's what you get. It's not done, but you get that. On the bottom, we're going to get 36 minus 25, which happens to be 11. No, that's not right.
I got 6
1?
minus 5.
6 minus 5 is 1. Come on, Foster. I'll do that in a minute. Okay. Actually, I'll do it right now. You're right.
You scare me.
I'm sorry. It's not Halloween yet. My grandkids, they do a theme and they're doing Harry Potter and they want me to go as Dumbledore. They want me to walk door to door with them. And I'm supposed to be Dumbledore somehow. Okay.
I'm watching Harry
Yeah.
Potter right now.
Oh, wait a minute. No, you're in math right now.
I mean, the TV's playing Harry Potter in the back.
Oh, okay. Yeah, TV, Disney Plus. If you get Disney Plus, has a lot of Harry Potter on it also. But and then all the Avengers stuff too. But yeah, I love Harry Potter. I absolutely love it. But I don't know how could I want to be Mad Eye Moody instead. You know, yeah. They don't want me to be that. Okay, so let's see if I can do this right. So I have radical 6, radical 5, radical 6 minus radical 5. So radical 6 is radical 36, which simplifies to normal 6. Radical 6 times that is negative radical 30, because you're doing inside, inside, outside, outside. This is positive radical 30. Inside, inside, outside, outside. This is negative radical 25. But the square root of 25 is 5, so minus 5. So you have 6 minus 5. So you do have a 1. Okay. Now, the only thing, this is almost done. Okay, except what about the square root of 12? It simplifies. Okay, go to your calculator. Remember, if you've got the TI 36X Pro, it will do that for you. But for us, square root of 12 is 4 times 3 using our factorization. Well, we know the square root of 4 is 2, so the square root of 12 is 2 radical 3. Square root of 12 becomes 2 times the square root of 3. But if it's got a 5 on there, it's just multiplying. 5 times 2. So this is 10 radical 3 minus 5 radical 10. And remember, for all fractions, okay, when it's the denominator is a 1, we don't write it anymore. We just say it's the numerator, whatever that was. Is that okay with everybody or not?
Yep.
Okay. Now okay. I'll keep pushing. I want to erase, move on to new material, not new material, but new review material, meaning solving equations. I'm hoping you guys, I saw a lot of people have been doing really well on the second chapter 8 stuff. A lot of people are way ahead on that, and some people aren't. Okay, but a lot of you were. So I'm hoping this is making sense to many of you. Okay. All right. Anything I can do about how, are you guys okay with how I distributed 5 radical 2 times radical 6 and 5 radical 2 times radical 5? You okay with that? Are you okay with how I simplified 5 radical 12 into 10 radical 3? Any questions at all on that? Okay, then the last thing we covered was radical equations. Okay, radical equations. Chapter, I think it was 8.7, I don't remember, whatever. First step was to isolate whatever the radical was. Isolate means get it alone. Actually, Bach came up after class. I screwed up a couple times last week. I forgot to take roll. I was planning on it. I had a roll sheet all ready to pass out, didn't. And Bach came up and he had a different way of doing the problem, which isn't wrong, but he didn't isolate the radical first, okay? And that caused all kinds of issues. You can get away with it, okay? But it's simpler if you do it this way. Okay, all kinds of problems happen, but isolate the radical to the best of your ability. The second was power both sides. Third was solve whatever the new equation is. And for us, I said we might have a linear equation. Linear means get x alone, or we might have a power equation, which means we must equal 0 and then factor. And that's up to you. You guys have to make that determination. After you power both sides, you got to decide, oh man, how do I solve this problem? And every problem is a little bit different. So you've got to apply analysis and critical thinking and all kinds of great things. But for our purposes right now, they're either going to be linear, that means no power, so you get x alone, or they're going to be power, which means we make it equal 0 and then we factor it. Okay, so we solve it. Fourth is we check for what's called extraneous solutions. Extraneous, the root word is extra. Okay, they're extra answers that don't work in the original. When you check your work, you always check your answers back in the original problem. And more than any other time, probably about 50% of the time, one of your answers will get rejected. I'm not sure which one. It's hard to predict, but in this particular process, it introduces lots of wrong answers. There's no other way to get around it. I mean, you can't avoid it. So you just work the process and then check your answers. And then lastly, you solution set. Okay, solution set the correct answer. So fifth, or solution set correct solutions. And again, there's no way of getting around extra answers, wrong answers. You just have to check your work. So with that, I have the square root of 6x minus 11 plus 7. Notice the 7 is not inside the square root, equals x plus 4. Okay, I want to do this one tonight. Tomorrow night, I'll maybe have another one for you guys to do as a review. But this has a couple good tricks in it. Or do you guys want to work on it? Anybody want to work on it and see how you do? I don't hear anybody yelling. Okay, so I do want to work on it because there's a few tricks here. So the first thing we want to do is get this radical alone, isolated. So we're going to take 7 away from both sides. That's going to give me the square root of 6x minus 11 equals x minus 3. Okay, so step 1, isolate the radical, whatever it was. Now, step 2, we need to power both sides. So this is where you have to recognize that this was a square root. And so the only thing that cancels out a square root is a square power. So you square power both sides. Okay. So on the left-hand side, this is easy. You get x minus 11. The square power and the square root cancel each other out. Square power, square root cancel each other out. But this is where the first mistake can come in. Right here. Okay. If you did that, you're done. Wrong, no credit. Because remember, you can't square the pieces. You can't take your power and say, oh, that's x squared and that's negative 3 squared. Remember, I had that big thing here that says never, never. You can't take a power, distribute it over a plus or a minus sign. So the only way to do this side, you're squaring the entire side, is to go off your scratch paper, set up a matrix, x3, x3, and if you set that matrix, you're going to get x squared minus 6x plus 9. Remember how we've done the x plus 3, you do the matrix x squared, you get 3x, 3x, 9. Oh, they're minus 3s. I'm sorry, x minus 3, x minus 3. I should have put that there. You have to get this. So there's the first mistake that students generally make, is they square this wrong. Okay, so anyway, now I'm looking at this going, what do I do now? Well, I've powered both sides. Now I have to study this, analyze it, and decide, okay, what kind of problem is this? Well, because it's got an x squared in it, I know it's a power equation, so it has to equal 0, and I have to end up factoring it. Okay, so I'm going to take away 6x away from both sides. I'm going to add 11 to both sides. And I'm going to get 0 equals x squared minus 12x plus 20. Again, after I power both sides, I need to study the problem. I need to analyze it. I need to think about it. Okay, how do I solve the new equation? Is it linear? Is it a power equation? Is it something weird? I don't know. In this case, it's power. But that's the determination you and only you can make. Okay, so it's now equal to 0. Okay, this is a power, so I can do the AC bit. So my AC is 20, because remember there's a 1 there. A times C is 20. So what times what makes 20 but adds to negative 12?
Negative 10, negative 2.
Yep. Negative 10, negative 2. Is that okay with everybody? Again, you can see how everything seems to come back to factoring. Factoring always is there. So remember, this was a simple, what I call a simple or an easy trinomial. So you could just go 0 equals x minus 10, x minus 2. You just use those. Split it up. X minus 10 equals 0, which means x is worth 10. Or x minus 2 equals 0, which means x is worth 2. Okay, so solve the new power equation. I did. I got my two answers, 10 and 2, but now I have to check. Okay. And I'm checking back in the original. That's 60. Take away 11 is 49. Square root of 49 is 7. Plus 7 is 14. But this is 10 plus 4 is also 14, so that looks like it's okay. 2. If x is 2. 6 times 2 is 12. 12 take away 11 is 1. Square root of 1 is 1. 1 plus 7 is 8. So I have 8. But x is 2. 2 plus 4 is 6. There's no way 8 equals 6. So this is a reject. And I'll go through this if you need me to and show you my steps about the checking. I'm trying to do the checking in my head. But on this particular problem, the 10 is the only answer. The 2 got rejected. Okay. Almost a guarantee of that kind of problem. I love this problem, guys. I know that sounds weird, okay? But I love it because of a couple things. Number one, I get to see, did you square both sides? Did you square that quantity correctly into that? That's trap number one. Number two, I love factoring. So this particular problem has a factoring step into it, which I think is cool. And number three, one of my answers rejected. Okay. So to me, this problem shows me a thinking person, a person who's really learned this part of algebra. They know how to square out a binomial. They know how to set it equal to 0, factor it, and they know how to plug things back in and check your solutions. I like this problem a lot. Okay, I'll do some more of those tomorrow, but I think we're pretty burned out. I want to take about, well, let's say a 5-minute break right now, and then we'll come back and learn something completely, totally, 100% new. 100%. You've never seen it before, most of you. So let's take a break. 5 minutes. Okay. I feel I have to give you a little bit of a historical insight, although this is not going to be, I'm not going to test you on the history where this came from. But there's something called the fundamental theorem of algebra. And it's much more complicated than what I'm showing you right now. But it basically says, if you have, if you have an equation with whose highest power is 3, you're going to have 3 solutions, maybe less than that, but you could predict 3 solutions. Okay, and think about this: x squared plus 6x plus 12 equals 0. When we had a problem with power of 2, we had 2 solutions. Okay, And so the fundamental theorem of algebra was proven 600 or 700 years ago. And it tells us that we can very accurately predict how many solutions an equation will have. Now, again, like I said, I'm kind of cutting out a lot of the nitty-gritty stuff, but that's pretty much it. Okay, if you have a third power equation, then you're gonna have 3 solutions. Maybe 1, but whatever. If you have a second power solution or equation, you're gonna have 2 solutions, and so on. Well, everybody goes, yeah, and they all like that proof. And then somebody came up and said, oh yeah, find the answers to that problem. It's supposed to have 2 solutions. Find them. And they couldn't. Okay, again, this is like 500 to 700 years ago. Okay, they thought they had the world under control. They thought mathematicians and scientists thought they knew everything. And then somebody said, yeah, find that one. And the answer is you can't. Well, let me show you why. Okay, because if you take this, okay, you get x squared equals -4. Okay, and from our arithmetic skill, we know that nothing times itself can equal a negative number. Nothing times itself can equal a negative number. Okay, but mathematicians said, but wait. This fundamental theorem is correct. So they said there must be something wrong with our understanding of mathematics, our fundamental understanding, because this is correct. And we've used this in all kinds of situations, this fundamental theorem. And it's never failed us until here. So there must be something wrong. I mean, this is the ultimate definition of science. You come up with a theory, you come up with a hypothesis, and you use it until something fails. And then you adjust things. That's what science is all about. That's what math is all about. Okay. So they came back and they said, how can somebody times itself be negative? It can't. There's a screw up somewhere. So with that, mathematicians went back to the drawing board and they figured out that their understanding of numbers was wrong. Or maybe I should say was limited. And now we go back to something we kind of discussed near the first of the semester. We have what are called the real numbers. And the real numbers are made up of everything on the number line. Everything on the number line. All the square roots, all the decimals, all the fractions. We can divide the real numbers into 2 major categories. We have the rational numbers. Now we're talking numbers now. Rational numbers or irrational numbers. Rational numbers are like 2/3. Okay, 5.7. -0.6 repeating. Those are all rational numbers. And there's various ways to describe a rational number. You can say they can all be written as a fraction, where the top number is an integer and the bottom number is an integer. Or you could say when you look at their decimal either stops, 5.7, or repeats a pattern. Okay, so there's a lot of ways to look at rational numbers. Irrational numbers, okay, are like the square root of 7, negative square root of 3, pi. Okay, some of you have heard of E. We'll get those. Those are irrational numbers. And essentially, they're decimal numbers. If you pop pi or square root of 7 or square root of 3 or anything like that into your calculator, the decimal approximation, if you press the FD key on your calculator, okay, the decimal approximation goes forever. Now, obviously, your screen isn't big enough, but it's proven on supercomputers and all that kind of crud that, yeah, they go forever. So mathematicians back in the day thought they knew everything. Real numbers are made up of rational numbers and integers, and we're happy. And then that smart aleck came by and said, yeah, what's the answer to this? Okay. And they go, we blew it. Okay. Because the answer to that is not real, meaning it doesn't fall into these categories. Okay. Not real. So they said, mathematicians go, well, if something isn't real, what else is it? What's the opposite of real? If it's not real, and they said, there must be a whole other category of numbers that we'll call imaginary. Now, mathematicians thought that was pretty funny. Math teachers have hated it ever since, because when you call a number imaginary, students think they're stupid, they're unimportant. They're like those little people I talk to at night before I go to bed. Okay? Imaginary. Unfortunately, imaginary numbers exist and they're necessary. They're necessary for all of our calculations about the universe, black holes, okay? Singularities. Stephen Hawking's made, how many awards did he receive for being able to prove stuff about black holes and singularities? All of our nuclear physics depends on imaginary numbers. Well, it depends on more than that, but imaginary numbers are kind of really important to it. So they're useful. They have this unfortunate name. Okay. Imaginary numbers come from the idea. This is where, if you haven't been taking notes, this is where you want to start taking notes right now. Imaginary numbers come from the idea that if we take the square root of a negative number, now this is only for square roots, not cube roots, not fourth roots, not fifth roots, only square roots. The square root of a negative number is imaginary. So, for example, if you're doing a problem and you run across the square root of -5, we instantly, excuse me, I called that wrong. Okay, well, that's okay. The square root of -5, we instantly take out what's called an I and call it the square root of regular 5. But that I there is a designation that it's an imaginary number. It belongs in this category, not in this category. It's not a real number, it's in the imaginaries. Okay, square root of -5. Now, before this, we said, no, you can't take the square root of a negative. Now we're saying you can. In fact, you must, and you must call it an I. So there's a rule, and I'm going to show you more things. The instant, and I can't stress that enough, the instant you see a negative inside of a square root, you take it out and call it I of the normal square root, and then you work from there. So for example, if you have the square root of -12, well, the first thing you do is call it I times the square root of 12. Have to. You don't wait one step. You don't go, oh, okay, it's the end of the problem. I better shove an I in there to make Foster happy. No, no, no. You take it out now. Okay, but now we look at this, and the square root of 12, we know, is 2 radical 3. We've been doing that a lot, and your calculator will do that. But remember, these are all multiplying. 2 times I times radical 3. So mathematicians have said, okay, we want to call this 2I radical 3. And we're going to run into a little bit of problem because mathematicians have broken their own rules. I'll explain what I mean in a minute. Okay. But that's the basic idea. When we're looking at the square root of a negative number, and remember, I can't stress enough, it must be the square root only, not cube root, not fourth root, square root. The square root of a negative number means we're dealing with imaginary values. Imaginary doesn't mean impossible, it just means not real. Okay, and so the rule is the minute you see a negative sign inside of a square root, you take the negative out and call it an I. And then you deal with the rest of the square root. Okay, now there is a definition that we work with, a definition. Mathematicians will say the square root of -1, the square root of -1 is worth I. Okay, that's how they defined it. I'm just showing you kind of the end result, but that's how a mathematician defines I. I is the square root of a negative number. Square root of -1 is I. Now, an interesting thing happens, at least for us in math. If you take this, if you accept that the square root of -1 is I, what happens when you square both sides? If you square this side and square this side, by squaring both sides, the square cancels the square root. Remember, that was the square root. So that you get -1 equals I squared. Okay, that's what most people remember. For your purposes, this is the definition. This is the most useful. This is called this is the definition up here. This is what mathematicians write in all their books that everybody falls asleep over trying to read. The square root of -1 is I. That's where it comes from. That's how we defined it. But how do we actually use it? We use this idea. I to the second power is worth -1. So let me show you how that works. Okay. Yeah, I should have erased that. Oh well. So suppose somebody had the square root of -6 times the square root of -2. Okay. Now, if you used the inside, inside, outside, outside, you'd have the square root of -6 times -2. You'd have the square root of 12, which we know simplifies into 2 radical 3. I just did it. You can use your calculator to do it. But, okay, I should tell you right now, this is wrong. Wrong. Because I told you a few minutes ago, the instant you see a negative inside of a square root, you have to take it out and call it I. So the square root of -6 becomes I times the square root of regular 6 times I times the square root of 2. So the negative comes out and we write an I on the outside. The negative on the 6 comes out and we write an I on the outside. Okay, now if we use the outside, outside, inside, inside rule, okay, we end up with I squared, because I times I, anybody times itself is squared, times the square root of 12. Inside, inside. Outside, outside, inside, inside. So this becomes -1 times, and we've talked about the square root of 12 is 2 times the square root of 3. So put all this together, this is negative square root of 3. -2 square root of 3, I'm sorry. And this is the correct answer. Okay, so before I entertain questions in a second, I got a lot more to show you, but this is the problem, and I've shown it using 2 methods. There's the problem. Okay, the first one, I just multiplied outside, outside, inside, inside. Square root of 6 times 6 times 2 is 12 positive. Square root of positive 12 is 2 radical 3. But it was wrong because, okay, the instant you see a negative inside of a radical, you have to pull the negative out and call it an I. So when we multiplied this, then we really did have an outside, outside. I times I is I squared. 6 times 2 is 12 on the inside. Clean up the inside. The square root of 12 is 2 radical 3 times the -1, because we use I squared is worth -1 right there. I squared is worth -1. So there's our final answer. All right. Let me pause. And are there any questions so far? I'm going to do some more problems and give you some practice here. And over chapter 9, okay, this is section 9.0. I termed it that. It's like an introduction to chapter 9. All of our equations, and that's wrong. Many of our equations will have imaginary answers. So this isn't something that we can just go, okay, it's stupid imaginary numbers, and I'll get through this and don't worry about it. This entire chapter, chapter 9, and some of chapter 10, okay, is going to involve complex numbers, imaginary numbers. Oh, I didn't talk about complex, imaginary numbers. So questions? You're sure? Okay. I need to erase the board. This is the 2 concepts you need to take so far. The fundamental ones is you need to notice to take the I out instantly. If you see a negative inside of a square root, that's number 1 concept, key. And number 2 concept is if you ever have I to the 2nd power, you replace it with -1. I to the 2nd power equals -1. Those are the 2 concepts that you should have taken out of everything I've been babbling about for the last 15 minutes. Okay. Little bit more number theory back. We're going to go back. We talked about there are real numbers, and these are numbers on the number line. There are imaginary numbers. Okay, and this is what, when you have the square root of a negative, that's imaginary number. Okay, and mathematicians decided, we can separate the reals over here. We can separate the imaginaries here. But what if we want to talk about them as one big giant group of numbers? Then they introduce something, a new concept called the complex number system. And so the new vocabulary word is called complex numbers. And a complex number is written as A plus or minus BI. A complex number is a combination of a real number plus or minus an imaginary number. Okay? The real number must always come first. The imaginary number always comes second. So, for example, if I write 5, this is a real number. If I write 2i, this is an imaginary number. But if I write 5 plus 2i, this is called a complex number. Okay, some people add the word pure. If I write 5, this is a pure real number. It's real and only real. If I write 2i, it's imaginary. It's a pure imaginary. There is no real to it. It's just imaginary. But if I write 5 plus 2i, or I write, it doesn't matter if I wrote 5 minus 2i, then I would have a complex number, real, joined somehow with an imaginary, plus or minus the imaginary. So 5 is called the real part. The 2, or the -2, is called the imaginary part. Okay, so we have a complex number, which is a combination of reals and imaginaries, separated by a plus or a minus. Okay, and you're going to read that in your vocabulary. The directions in Mom in chapter 9, which is now open for those of you who are going to go ignore me right now. Chapter 9 is open. All the homework for chapter 9 is there. Okay, but there's some tricks, so don't get too far ahead of me. There's some problems. Now, there's a really kind of an important idea. In general, okay, tradition says put I at the end of a number. So think about this. We wouldn't write x2, we would write 2x. Okay, so we wouldn't write I2, we would write 2i. Okay, notice you've been brainwashed, you've been taught to always put the x's and the y's at the back end and the coefficient at the front of a number. Well, I works exactly the same way. Okay, I times 2 is 2 times I, but these are better. These are best practices. Except, oh, brother, except for radical numbers. Okay, I'm running out of room. Okay. Well, let's see if I can squeeze it in a little bit. So this is our general rule. Tradition says we always put the I at the end of the number. Always put the I at the end of the number, just like you put the X at the end of the number. You put the I at the end of the number, unless you have a radical. So if you recall, I just did a problem a second ago where I had the square root of -12. Okay. And the first thing I did is I took the I out. And then I said, okay, the square root of 12 becomes 2 radical 3. And so I wrote the answer as 2i radical 3. And that is the answer. So the exception is you put I in the front of a radical, but you put it in the back of any other number. Why? Because you will find there is a time when we will have I inside the radical. When you hit pre-calculus and well, it wouldn't be calculus, but when you hit pre-calculus, you might end up with the problem asking you to the square root of 3i, where the I is inside. And so we don't want to confuse the issue. If we want the I inside a radical, we put it inside. But if we want the I out of the radical, we put it in front. Okay, and people wonder why students hate math. So if it's a normal looking number, you put the I in the back. If it's a radical number, you put the I in the front. That's it. Okay. Questions?
Professor, I have one question.
Yeah.
So earlier when you were going over the examples, you did the -6 times -2i, and the answer for that was -2 square root of 3. Wouldn't technically the square root of -12 be the same as the -6 times -2?
Yes.
So
Well,
technically
wait a
that answer would be -2 square root 3.
No. Okay, wait a minute. Let's start again. Okay. So we started with square root of -6 times the square root of -2. Right?
Correct.
Okay. That was never the square root of -12.
Okay, never mind. I see where I messed up. I get it now.
It's square root of +12.
Yeah, I see where I
Okay.
messed up now. Makes sense.
Okay. All right. Anybody else? There's a lot here, guys. For most students, this is, if you took intermediate algebra in a class before, this is right about where your brain started turning off because you're going, this is too weird. Okay. So this is a great time to be asking questions. Okay. Well, with all of this, we can ask all kinds of fun questions. 3 parentheses 5 plus 2i minus 7 parentheses 6 minus 4i. Okay, this is called complex arithmetic. You're going to add or subtract the two numbers together. So pretty clearly, this is 15 plus 10i. 3 times 5, 3 times 2. That's 6i, idiot. Pretty clearly, I'm losing it. Come on. God. This is minus 42 plus 28i. I got that one right. So we distribute the -7 here. And we distribute the 3 here. Okay. And then we say, okay, are there like terms? Yeah. 15 and 42, those are real numbers. So they can be added together to make -27. 15 take away 42 is -27. That's the real number. Okay. 6i and 28i, that's the complex number. So plus 34 i's. Okay, not I squared. I squared only comes if you multiply them. If you had 6i multiplied by 28i, then you'd get an I squared in there. There's no I squared, so that's the answer. Okay. So what if I had something like 4 minus 2i times 3 plus 5i? Actually, you guys try that one. 4 minus 2i times 3 plus 5i. And we've seen how much fun I have when things are happening in my head. You'd think maybe when I fell off the ladder and ruptured my Achilles, maybe I hit my head. Yeah, that's my excuse and I'm sticking to it. Okay. So let's see if my answer is correct. So 4 minus 2i times 3 plus 5i, set up the matrix box. 4 times 3 is 12. 4 times 5i is 20i. Negative 2 times 3 is negative 6i. Be careful. And negative 2 times 5, I think I'm wrong, is negative 10i squared. I think my answer is wrong. Okay, so first question, are you guys okay with my matrix? I'm not done with it at all. I'm not done with the matrix at all. 4 times 3 is 12, 4 times 5i is 20i, negative 2i times 3 is negative 6i, negative 2i times 5i is negative 10i squared. Is that okay with everybody, my math? Okay. What about negative 10i squared? Negative 10i to the second. What does I, well, I'm right. Huh, I'll be damned. Darn. What does I squared worth? This is negative 10 times negative 1. Negative 10 I squared is negative 10 times negative 1, because I squared is worth negative 1. That was a key formula or rule that you had to know. So this becomes positive 10. So what do I have? I have 12 plus 10 is 22. That's my real numbers. And negative 6 and 20 is positive 14i. That's my imaginary numbers. Okay, so I was half wrong. Okay, that would be the answer. This is the answer to this. Yes or no? I screwed up a sign. Is that kind of okay? Okay, the key here is that you got I squared, and you have to remember I squared is worth negative 1. So when you have negative 10 times I squared, you have negative 10 times the negative 1, which was positive 10. Okay,
I got a
try this
question.
one. Yeah, shoot.
In the notes, he said the square root of -1 equals I squared.
No, the square root of negative 1 equals I. The square root of negative 1 equals I. But if you square both sides, then the square cancels the square root, so you just get plain old negative 1 equals I squared. The square root of negative 1 equals I. But negative 1, no square roots, equals I squared. Double check your
Thank you.
notes. You okay with that? I mean, if I said that, I was wrong. I'm pretty sure I wrote this though. I may have said it, but I wrote it. I wrote it right. I may have said it wrong. I don't know. So this top one here, without the red, this is what I call the definition. This is where I comes from. The square root of -1 is I. That's called our definition. A definition is kind of like the 10 Commandments. You know, God handed Moses supposedly these 10 Commandments in stone, and we can't question them. God says, so we go, okay, fine, whatever God says. Okay, that's a definition. Okay, can't question that it is. But by squaring both sides, we get this formula, and this is the useful part of it. This is what we actually use. We kind of say, okay, there's definition, but this is the part that we really use in all these problems. Anybody? Did that clear up your question or not, or did I just screw it up more?
Very good, thank you.
Okay. All right. You guys try this one. 3 minus 2i quantity squared. 3 minus 2i quantity squared. Oops, we're recording. I should have paused this. Oh, well, we'll work it out. 3 minus 2i. 3 minus 2i. This is 9. So the real key is what happens here with 4i squared. Right there. That's 4 times -1. So 4i squared is actually -4. So add like terms. Okay. -6, -6, -12i. 9 take away 4 is 5. And that is wrong. Okay. My numbers are correct, but I'm trying to make a point of something. Okay. 9 take away 4 is 5. So my real number is 5. Okay. -6i, -6i is -12i. My imaginary part is -12i. Okay. I've made no mistakes, but my answer is still wrong. I'll show you why. Okay. So as I find my junk. Okay. Remember, I said there's the real numbers. Oops, spelled wrong. And there's the imaginary numbers. Okay. And then mathematicians invented a new word called complex to talk about the two of them together. There's real numbers, there's imaginary, but what if I want to talk about all of them? Then we use the word complex numbers. Okay. And I wrote up here, complex numbers are written as A plus or minus BI. And I said, okay, that A is the real part. A represents the real number, and BI or B is the imaginary part with the I on it. So B is the imaginary numbers. The implication here is that you always put the real number first. And that's just a math idiosyncrasy. Okay. Always put the real number first. Okay. So even though this is 100% correct, okay, you must write it as 5 minus 12i, because you must put the real number first and the imaginary number second. And again, the word idiosyncratic, I can't even say it now. It's the root word is idiot. The fact that you have to follow these rules, okay, it's important, okay, but it's kind of drives you crazy at the same time. Okay. We're going to do a little bit more on chapter 9 tomorrow, 9.0, and then we'll get into the main part of chapter 9 tomorrow, including something called the quadratic formula. Okay, so chapter 9.0, we'll do more of it tomorrow. Then we'll learn the regular part of chapter 9. And I hope you guys come with questions about chapter 8, roots and radicals. Okay, because we have Thursday quiz. All right. I am not taking roll. See you guys. Bye-bye. Hasta mañana.
Thank you, Professor.
Night-night.
I got a question.
Yeah.
Do you mind just emailing us like each quiz section? Like quiz 1 will cover 8 point something to 8.3.
Sure. Sure.
Okay.
You want me to just set
Thank
that
you.
one up? Yeah.
Please.
Let me write myself a note. Do you want me to email it, or do you want me to put it in an announcement? What would you prefer?
Either or, whatever is better.
Okay. I know I send a lot of emails and I usually feel bad about it. Okay, but email somehow. I'll think about what I want to do. Email quizzes, quiz covered. Okay. Probably I'll get it out tomorrow morning. Is that okay?
Yes, thank you. I just like to separate my studying. So
I understand. Okay. The first 3 seconds, I guarantee it's quiz number 1 is going to cover 8.1, 8.2, 8.3. I'm almost certain, but I'll look at it and double check.
thank you.
Yep. All right. Anybody else still there?
I have a question too.
Sure.
Buddies,